Okay, so we are going to start doing some examples here. We've laid the groundwork. We've talked about how to solve homogeneous Cauchy-Euler equations, and even though we were focusing exclusively on second-order equations, we're going to see that we can apply these techniques to higher-order ones as well. But to start, let's try solving one. So here's an equation that I want to solve: x y double prime minus 3y prime equals 0. Be careful, okay? So don't just jump right in. You need to know that you're looking at a Cauchy-Euler equation here. And if you're paying attention, you should see that you're not. This is not Cauchy-Euler because the power on my x does not match the power on my derivative here, nor does it here. However, if you multiply both sides of this equation by x, you make it into a Cauchy-Euler equation. So I get x squared y double prime minus 3x y prime equals 0. And notice both terms have the required coefficients. They have powers of x that match those derivatives. So that's good to know because, again, like we said in the beginning of the last video, the restriction that we place on these coefficients is very, very strict. However, there are some cases where we may not start with a Cauchy-Euler equation, but we can change it into one. Okay. Now, what do we need to do? Well, the goal here is going to be to come up with that quadratic equation that we showed on the previous page, solve it, and then see what case we're looking at and find a general solution from there. And you're going to find this goes pretty quick. But what I'm going to do, rather than use the quadratic equation as we derived it before, at least for this first example, I want to go through the derivation of it. I'm not going to do that every time, but I am going to do that here. We're assuming that our solution has the form y equals x to the m, which means y prime equals m x to the m minus 1, and y double prime is going to equal m minus 1 x to the m minus 2. I would like to substitute those into my Cauchy-Euler equation, which is right here. It's this guy. Okay, so that means I'm looking at x squared times y double prime, which we just found was m times m minus 1, x to the m minus 2, minus 3y prime, so that's minus 3 x, sorry, it's 3xy prime, so minus 3x times y prime, which was m x to the m minus 1, and that should equal 0. Okay? And as we saw before, when I multiply, parenthesis right there, when I multiply that x squared in and when I multiply that x in, both of these terms will produce an x to the m. So that's going to be factored out, x to the m, and then I'm left with m times m minus 1 minus 3m in there, and that's equal to 0. Remember, we really just need this guy to equal 0. So if I do that, and if I distribute that m in, I'm going to get m squared minus m minus 3m, so that'd be minus 4m equals 0, or m times m minus 4 equals 0. And then this gives me solutions m equals 0 or 4. Okay, and I'm basically done here because we already showed that what the solution will look like in the case of distinct real roots like what we have here. Y will equal c1 x to the power of 0, which is just 1, so I'm going to call that c1 and just leave it at that, plus c2 x to the power of 4. Okay, considering how long some of the problems have taken in previous sections, in recent sections, this is kind of refreshing. It's not that much work, really. Okay, let's try another one. I would like to solve this equation. Notice this one is already Cauchy-Euler as written. You can verify that. And it's homogeneous, so we can use what we've come up with. In this case, I'm not going to go through the process of doing this. I'm going to just use the equation that we came up with before. So our Cauchy-Euler equation will produce the following quadratic that we need to solve. M times m minus 1. Remember, and then it's going to be plus bm. So I'm going to actually show you that equation here. We're using this guy right here. So a m times m minus 1 A in this case was 1, which is why I didn't write it, minus bm, so that's, or plus bm, that's going to be minus 7m plus 41 equals 0, okay? Let's distribute that m in and combine some like terms. This becomes m squared minus 8m plus 41 equals 0, okay? Yeah, it's pretty easy to see. This thing does not factor nicely. 41 is a prime number, so there's not a whole lot of factors of this thing to check. This will not factor conveniently, so we go straight to our quadratic formula for this one. M is going to equal negative b, so that's 8, plus or minus the square root of b squared, negative 8 squared is 64, minus 4ac, minus 4 times 1 times 41, which is 164. All over 2a, which is just 2, okay? That comes out to a negative 100 in there. The square root of negative 100 is 10i, so I'll get 8 plus or minus 10i over 2. Dividing by 2 gives me 4 plus or minus 5i, okay? So now we're looking at a case 3 situation, and again, you know, we've actually done all the work that we need to do, because we know exactly what to do with these numbers. According to what we found in the previous video, y is going to equal c1, sorry, actually, let's do this. Y is going to equal x to the 4th, and I'm going to do something here too. Let me find that solution. Oh, no, it's on this page actually. So up here I gave my general solution. I'm noticing that both of these terms have the same x to the a in them. I'm just going to factor that out to keep things a tad simpler. X to the 4th, where did you go? Cosine of b natural log of x. So b is 5 natural log of x, plus sine 5 natural log of x. And that's it. Again, it's refreshing, right? Because that went really quick. And in this class, you don't get that very often. Problems seem to take a while. I have a blank page in here for some reason. Set that aside. All right, let's try another one. This one's an IVP, so we have some initial conditions to check. But again, before you do anything, you need to make sure you're looking at a Cauchy-Euler equation. Is that what we have? Yes, I can see the power on my x's matching the derivatives. We're in good shape, okay? So once again, I already know what that quadratic equation is supposed to look like. M times m minus 1 plus bm, so that would be minus 3m in this case, plus 4 from this guy. Okay, that equals 0. Multiply that m through. That's going to be m squared minus m minus 3m. That's minus 4m plus 4 equals 0. But this guy factors to m minus 2 squared equals 0, which gives me m equals 2, and that's going to have multiplicity 2. It's a repeated real root. So now we're looking at case 2 of the work that we did previously. Okay? So what kind of a solution does this create for us? Well, it's going to give us y equals c1 x to that power, so x squared, plus c2 x squared natural log of x. That's what we came up with. Now we're not done because remember we have initial conditions. We have y1 equals 5 and y prime of 1 equals 3. In order to use that second initial condition, I will need a derivative. So let's find y prime next. Y prime equals 2c1x plus, I need the product rule here. So that's going to look like 2c2x natural log of x plus the derivative of the natural log of x is 1 over x, which cancels one of those x's. That just gives me a c2x right there. Okay? Now let's take a look at our initial conditions. Y of 1 equals 5. What does that tell me? Well, put a 5 in for y there. Let's do this the other way around. Let's plug a 1 in for my x's. That's going to give me a c1. And then natural log of 1 equals 0. So that whole thing goes to 0. Y is equal to 5. And that's kind of cool. I actually got one of my parameters right away. C1 is equal to 5. Y prime of 1 equals 3 was the other guy. So plugging 1 into y prime, I'm going to get 2c1 right there. That natural log is going to go to 0, so I lose that term in the middle. And then c2 times 1 is c2, so that makes plus c2. And we want that to equal 3. Now, using the fact that c1 is equal to 5 makes this a 10. c2 would have to equal negative 7 for that to come out to 3, so negative 7. Okay? Now we can put those parameters into our general solution, and we have our final answer. Y is equal to 5 x squared minus 7x squared natural log of x. Okay? Not too bad. Not too bad. On to the next example. I wanted to look at a higher order equation, not much higher, just a third degree or third order equation as opposed to a second order equation, and just see what that's going to look like. So this one's not an IVP. We just want a general solution to this equation here. Check and make sure that you're looking at something that's Cauchy-Euler. Does the power on the x match the derivatives in each term? And it does. So we're good. We're golden. Now, let's see what we would need to do to solve this. So in this case, I don't want to just regurgitate that quadratic equation I've been starting with in the last two examples, because it's not going to look the same here. I actually need to go through the derivation process to get a different equation this time. We're going to, once again, assume that y takes the form x to the m, which means y prime is going to equal m, x to the m minus 1, and y double prime is going to equal m times m minus 1 times, I don't know why I'm putting parentheses there, x to the m minus 2. But we need a third derivative on our y also. So I need to continue differentiating. This is going to be y triple prime equals m times m minus 1 times m minus 2, x to the m minus 3. Okay? So we have to plug all of this stuff in where it would go in our DE. Our DE doesn't actually use y double prime, so I'm not going to have to plug that one in, but the other three are going to show up. Let's plug this stuff into our DE up here. Okay, I'm going to get x cubed, y triple prime, that's this guy. M times m minus 1 times m minus 2, x to the m minus 3 power, plus xy prime. Y prime was this guy, so mx to the m minus 1, minus y, which is x to the m, and that equals 0. Okay, pull the, first of all, make note of the fact that in each of these cases, multiplying this monomial on the outside to the monomial on the inside is going to produce x to the m for all of these terms. So I can factor that x to the m out, leaving me with m times m minus 1 times m minus 2 plus m minus 1 equals 0. We set this guy equal to 0, but let's distribute and combine a bunch of like terms here. So this is going to multiply out after doing the algebra to m cubed minus 3m squared plus 3m minus 1 equals 0. Okay? It's a cubic equation, which, remember, those are generally a little more difficult to factor. You can factor this using the rational root theorem, or if you remember your binomial theorem from back in algebra or pre-calculus, wherever you learned that, the form of this thing should look really, really familiar. The coefficients on these guys should look like they came straight out of Pascal's triangle, if you remember Pascal's triangle. Just, you know, with some negatives thrown in. If you remember the binomial theorem, then it should take you precisely 1 second to factor this thing. This is m minus 1 cubed equals 0. If you don't remember the binomial theorem, which I'm not going to review here, you can factor it using the rational root theorem, which we have done before in this class. Okay, so that means that m equals 1 is my only solution, and it has a multiplicity of 3. Okay? That's case 2, but with a root that has a higher multiplicity than 2. And we showed back then what the solution would look like. So my general solution now is going to look like y equals. Where did I put that? Y equals c1x plus c2x natural log of x. And then again, because the multiplicity is 3, I need one more term here. c3x, and remember we start raising that natural log to powers, second power in this case. Okay, that would be my general solution. So we are cruising right along. These problems do not take that much time, and we're doing a pretty good job here. So we've only dealt with homogeneous equations up until this point. We do need to examine how to solve non-homogeneous cases, but we actually already have all the tools to do that. Suppose we want to solve a non-homogeneous Cauchy-Euler equation. Well, that means that we need a complementary solution, which we have now talked about how to find. And then we also need a particular solution. But because Cauchy-Euler equations are linear, and because we now know how to find a complementary solution for them, we have all the tools we need to apply variation of parameters to find a particular solution. And so that's all that's left to do. If we want to solve a non-homogeneous Cauchy-Euler equation, solve the associated homogeneous equation using what we've done in the past 4 examples, and then use variation of parameters after that to get your particular solution. Now you have a general solution. Let's take a look at an example. So here is a non-homogeneous Cauchy-Euler equation, and as always, verify that it is Cauchy-Euler before doing anything else. It's easy to see that we have one here. Okay, I want to begin by solving this guy, x squared y double prime minus 2x y prime plus 2y equals 0, the associated homogeneous equation. Okay, this one is a second order equation, and we already know that we would be looking at this quadratic equation to get a solution here. M times m minus 1 minus 2m plus 2 equals 0, or m squared minus 3m plus 2 equals 0. Okay, this guy factors pretty nicely. We get m minus 2, m minus 1 equals 0, giving me m equals 1 or 2. So right away, we're looking at a case 1 of that homogeneous case. So we're looking at the following complementary solution. C1x plus C2x squared. Okay, not bad, not bad. Now we're going to use variation of parameters to get the particular solution that we need. So remember how variation of parameters works. We take our complementary solution and find the functions that make that thing up, x and x squared, and we're going to use those in the form of our particular solution. Okay, but to do that, we have to find those functions u1 and u2. So again, going through that process, we start by looking at the Wronskian of these two functions. We just call that w. That would equal, let's see, x squared 1, 2x. That's going to become 2x squared minus x squared, which is just x squared. Okay? Using our Wronskian in the variation of parameters formulas that we determined, u1 prime is going to equal negative f of x times y2, this function right here. So f of x is x to the 4th e to the x. Okay? y2 is x squared. And we put that over the Wronskian, x squared. So you're going to see the x squareds canceling out here. And, hold on, I want to make sure I'm not skipping something important. Yes, sorry, I need to back things up 1 second. Back up. I made a critical error here. One that I expect you guys are probably going to make also, even though I just caught myself. What do you have to do first thing when you're solving one of these DEs using variation of parameters? You have to make sure that your differential equation that you're solving has a leading coefficient of 1. In other words, you need to, in this case, divide everything by x squared first before you start using variation of parameters. It's essential that you do that. And I almost didn't do that. So this equation, we have to divide everything by x squared first. That means the equation that we're actually using variation of parameters on is this guy. Minus 2 over x y prime plus 2 over x squared y equals x squared e to the x instead of x to the fourth. I almost messed that up. Now you see where that's going to matter, because we're using this f of x in our variation of parameters formula, but I would have had the wrong power on that x in what I did up here. So don't make that mistake. Learn from my mistake so you don't have to use the extra time to fix it. Now we can find u1 prime. u1 prime is equal to negative f of x, which in this case is x squared e to the x, times y1, which is also x squared, all over x squared, and we see that simplifies down to just negative x squared e to the x. u2 prime, I have to find that next. u2 prime is equal to f of x times y1, so that's x squared e to the x times x over my Wronskian x squared. That simplifies to x e to the x. Okay? Now we need to integrate these. How do you integrate these? Well, u1 is going to equal the integral of negative x squared e to the x dx. And u2, we'll find that in a second. Now, this clearly requires integration by parts. And because I have an x squared on there, I can see that it's going to require at least a couple of iterations of integration by parts. You can do that if you want. You can go through the multiple steps. Or if you remember how tabular integration works from Calculus 2, you'll save yourself a pretty decent chunk of time. Sometimes they call this the DI method. If you remember what this is, all you're doing is you're taking the function that you want to be calling u, so that you'll find du by differentiating it, putting that here. Find the function that you want to call dv, which is my e to the x dx. Let's just use e to the x here. And in this column, I'm going to differentiate over and over again until I get to a 0. On this side, I'm going to be finding antiderivatives. So negative 2x, negative 2, 0. Those are all the derivatives I would have found. Integrating e to the x over and over again is just going to keep giving me e to the x. Then, if you remember what you do, you multiply things that are diagonal from each other. And you stop right before you get to that 0 term, because then it's just zeros each step of the way. And you get these alternating signs here. So I'm going to have a plus here, a minus here, and a plus here. Okay, what does that mean? Well, I'm going to have, when I'm multiplying this out, negative x squared times e to the x minus negative 2x, so that's plus 2x, e to the x, plus negative 2, so that's minus 2, e to the x. And that's it. That's what we're going to have. Okay? So tabular, if you forgot how tabular works, look it up, because it saves you a massive amount of time. Otherwise, I would have had to use integration by parts a couple of times, and that would have been a big time sink. u2 is equal to the integral of x e to the x, which we found here. X e to the x dx. I could use tabular on that also, or I could just use integration by parts once. You know, it's kind of up to you, I guess. And in this case, you're just going to get x e to the x minus 1. Okay? Now, what do we do to get our particular solution? Well, remember, yp is equal to u1 times x1, or y1, which is x. Let me represent this with by factoring the e to the x out, and we're multiplying that by y1, which is x. So that's going to look like x e to the x times, what's left in there, negative x squared plus 2x minus 2. And then here I'm going to have plus y2 x squared times I don't know why I have parentheses there. That's supposed to be e to the x right there. Let's get rid of that. Plus x squared times, let's factor the e to the x out of that guy, and I get x minus 1. Okay? You can do a whole lot of simplifying here. If I actually took the time to distribute both of these guys back in, combine like terms, this whole thing is going to simplify down. Where did I write that down? Simply just to, I lost my place. E to the x squared minus 2x. And you can verify the algebra there. So now I have a particular solution. This guy, I have a complementary solution. That guy, let's put them together, and that gives me y equals c1x plus c2x squared plus e to the x times x squared minus 2x. Okay? That's going to be my final answer. Okay? We just have one last thing that we're going to cover, but I'm going to do that in the third video.